Hi, I am Arturo Gutierrez and I'm going to talk about transformation of a material. Well, the process is thermoplastic. It is a plastic material, a polymer that becomes pliable or moldable above a specific temperature and solidifies upon cooling. One major characteristic that is useful to understand when it comes to plastic prototype production and or plastic part manufacturing is the distinction between thermoplastic and thermoset material. To make a long story short, thermoplastic material can be melted, cured, melted again, cured again, and so forth. There is a limit to the number of times this process can be repeated depending on the particulars of the given material, but the point is that thermoplastic material can be melted multiple times without significantly degrading the material. Thermoset materials, by contrast, can only be melted once. After a thermoset material cools, attempting to heat it again to its melting point will cause it to burn the material. It is useful to think of a two-part exposé when trying to understand the thermoset plastic. When it comes to injection molding, it's easy to misunderstand the relevancy of thermoset and thermoplastic materials. For starters, both thermoset and thermoplastic polymers can be injection molded. The primary difference applies after the injection mold cycle, when the molded plastic cures. During injection, molding plastic is heated and then injected into a metal tool. In order to physically get to the cavity, the molten plastic must first pass through a series of tunnels and entry points known as spruce, runners, and gates. Plastic cools every cycle within the mold cavity as well as within this channel that leads to the cavity. The material that solidifies is the spruce, runners, and gate. It is not part of the final product. It is essentially waste. I'm gonna give you a brief explanation about what is plastic, the material plastic. The term plastic includes material composed of various elements such as carbon, hydrogen, oxygen, nitrogen, chlorine, and sulfur. Plastics typically have high molecular weight, meaning each molecule can have thousands of atoms bound together. Naturally occurring materials such as wood, horn, and rosin are also composed of molecules of high molecular weight. The manufactured or synthetic plastic are often designed to mimic the properties of natural materials. Plastic, also called polymers, are produced by the conversion of natural products or by the synthesis from primary chemicals generally coming from oil, natural gas, or coal. Most plastics are based on the carbon atom. Silicones, which are based on the silicon atom, are an exception. The carbon atom can link to other atoms with up to 4 chemical bonds. When all of the bonds are to other carbon atoms, diamonds or graphite or carbon black soot may result. For plastic, the carbon atoms are also connected to the aforementioned after mentioned hydrogen, oxygen, nitrogen, chlorine, or sulfur. When the connection of atoms result in long chains, like pearls on a string of pearls, the polymer is called thermoplast. The metal injection molding is another process to transform a material. It is a metal working process in which finally powdered metal is mixed with binder material to create a feedstock that is then shaped and solidified using injection molding. The molding process allows high volume, complex parts to be shaped in a single step. After molding, the part undergoes conditioning operation to remove the binder and densify the powders. Finished products are small components used in many industries and applications. Due to current equipment limitation, products must be molded using quantities of 100 grams or less per shot into the mold. This shot can be distributed into multiple cavities, making metal injection molding most cost effective for small, intricate, high volume products which would otherwise be expensive to produce. I'm gonna give you a little bit history about material metal. A metal is a material that is typically hard when in solid state, opaque, shiny, and has good electrical and thermal conductivity. Metal are generally malleable, that is, they can be hammered or pressed permanently out of shape without breaking or cracking, as well as fusible and ductile. Around 90 of the 118 elements in the periodic table are metals. The others are nonmetals or metalloids. Though elements near the boundaries of each category have been assigned variably to either. Some elements appear in both metallic and non-metallic form. Astrophysicists use the term metal to refer collectively to all elements in a star that are heavier than the lightest two, hydrogen and helium, and not just traditional metal. A star fuses lighter atoms, mostly hydrogen and helium, to make heavier atoms over its lifetime. Used in that sense, the metallicity of an astronomical object is the proportion of its matter made up of the heavier chemical elements. Many elements and compounds that are not normally classified as metal become metallic under high pressure. These are formed as metallic allotropes of nonmetals. For example, physicists were able to keep hydrogen in its solid state under more than 3 million times the atmospheric pressure and deduce its metallic properties. The strength and resilience of metal had led to their frequent use in high-rise building and bridge construction, as well as most vehicles, many homes appliances, tube pipes, non-illuminated signs, and railroad tracks. Precious metals were historically used as coinage. A hammer forge was a workshop in the pre-industrial era that was typically used to manufacture semi-finished wrought iron products or sometimes finished agricultural or mining tools or military weapons. The feature that gave its name to this workshop was the water-driven trip hammer or set of hammers used in the process. The shaft or help of the hammer was pivoted by in the middle and the hammer head was lifted by the action of cams set on a rotating camshaft that periodically depressed the end of the shaft. As it rose and fell, the head of the hammer described an arc. The face of the hammer was made of iron for durability. Um, These hammers were originally driven by water wheels, but later also by steam power became increasingly common as tools became heavier over time, therefore more difficult to manufacture by hand. Some of the products that hammer forge made is with the iron. You can make a sword with iron using these techniques, and iron and you can also make broke iron, that is an iron alloy with a very low carbon content. In contrast to cast iron, it is semi-fused mass of iron with fibrous slag inclusion, which give it a grain resembling wood that is visible when it is etched or bent to the point of failure. Broke iron is tough, malleable, ductile, corrosion resistant, and easily welded. Before the development of effective methods of steel making and the availability of large quantity of steel, broke iron was the most common form of malleable iron. It was given the name broke because it was hammered, rolled, or otherwise worked with while hot enough to expel molten slag. The modern functional equivalent of broke iron is mild or low carbon steel. Neither broke iron nor mild steel contain enough carbon to be hardenable by heating and quenching. Historically, a modest amount of broke iron was refined into steel, which was used mainly to produce swords, cutlery, chisels, axes, and other edge tools, as well as spring and files. The demand for broke iron reached its peak in the 60s, being in high demand for ironclad, warship, and railway use. However, as properties such as brittleness of mill steel improved with better fabric metallurgy, and as steel became less costly to make thanks to the Bessemer process and the Siemens Martin process, the use of broke iron declined. Many items before they came to be made of mild steel were produced from broke iron, including rivets, nails, wire, chains, rails, grind wheels, coupling, water and steam pipes, nuts, bolts, horse handrails, wagon tires, strap for timber root cruiser, and ornamental ironwork, among many other things. Laser engraving, which is a subset of laser marking, is the practice of using laser to engrave an object. Laser marking, on the other hand, is a broader category of metal to leave marks on an object, which also includes color change due to chemical molecular alteration, charring, foaming, melting, ablation, and more. The techniques do not involve the use of inks, not thus involve tools, meats which contract the engraving surface and wear out, giving it an advantage over alternative engraving or marking technologies where inks or bead heads have to be replaced regularly. Some of the material that you can change with these techniques are natural materials. The marking of organic material like wood is based on material carbonization, which produce darkening of the surface and marks with high contrast. Directly burning image of on woods were some of the first use of engraving laser. The laser power required here is often less than 10 watts, depending on the laser being used, and most are different. Hardwoods like walnut, mahogany, and maple produce good results. Softwoods can be used judicially engraved but tend to vaporize at less consistent depths. Burning a softwood with a fan blowing on it requires lowest power, quickest speed of cut, and enough airflow to extinguish what is trying meanwhile to ignite. Hard papers and fiberboard work well. Linty papers and newsprints are like softwoods. For fur is not engravable. Finished leather so can be laser engraved with a look very similar to hot brandy. Certain leaded rubber compounds can be laser engraved. For example, this can be used to fabricate linking stamp. Paper, paper masking tape is sometimes used as a pre-engraving overcoat on finished and resined wood, so that cleanup is a matter of picking the tape off and out of the engraved areas, which is easier than removing the sticky and smoky surrounds. Another another material that it can change is stone and glass. Stone and glass do not turn gaseous very easily as spec This makes them generally a better candidate for other means of engraving, most notably sand blasting or cutting using diamonds and water. But when a laser hits glass or stone, sometimes something else interesting happens. It fractures. Pores in the surface expose natural grains and crystalline stops which, when heated very quickly, can separate a microscopic sized chip from the surface because the hot piece is expanding relative to its surroundings. So lasers are indeed used to engrave on glass, and if the power, speed and focus are used right, excellent result can be achieved. One should avoid large field areas in glass engraving because the result across an expanse tend to be uneven. The glass ablation simply cannot be depend on for visual consistency, which may be disadvantage or an advantage depending on the circumstance and the desired effect.